All right, guys, 4.3, we're going to talk more about trig functions. This time, we're not just relating them inside of triangles. So we're going to start trying to take this in a little bit of a different direction because triangles, that's great and everything. But if we can apply the same information in just two slightly different circumstances, it opens up a whole new world of things that we can do with this trig. So this is a pretty big lesson. It may end up being up to 3 videos long. It just kind of depends on how long these are taking. So I'll kind of decide that as I'm recording. But so just keep in mind, this is a really large section. This is also the section in which we are going to complete the unit circle. So definitely make sure that you stay tuned so that you can get that thing completed, because we will be testing on that at a later date. So, all right, without further ado, let's go. So what you're seeing on your screen are some more definitions. Angles are not only found in triangles. You can find angles in all kinds of different things, and you would have seen that in geometry. But here, we're going to specifically look at a kind of angle that you probably haven't really done before. This is what we call angles in standard position. These are angles. They've got a vertex at the origin. We're going to always say that the initial side, the starting side, is here on the positive x-axis. And then the terminal side is going to open up to wherever that terminal side is. And the degree at which that is open, that is what theta is, okay? Now, another really important thing, it is possible to have negative angles. What the negative will indicate is a direction. Just like a negative on a number line indicates that you're going to the left, a negative angle in this circumstance just means that you're opening in the opposite direction. So positive angles, they're always going to open counterclockwise. That's what you're seeing here in this picture. But if it happened to open down in the clockwise direction, that would be a negative angle. So just keep that in mind. It is possible to have both positive and negative. All right, so coterminal angles. Let's talk about what that is for a moment. Coterminal angles, they have the same initial and terminal sides, but they have different angle measures. So that would be things like if you look at 90 degrees, or what if I were to make a complete and total rotation from that 90 degrees. So this is a blank unit circle, but I want you to think about 90 degrees would be here, right? The starting side would be on this side, terminal side where my hand is right there. Now, if that's where 90 degrees was, but I went a full another 360 degrees, you would land in the exact same place. And that's what's considered a coterminal angle, because it lands in the exact same place. You'd still have the same initial side. You'd still have the same terminal side. It's just that in order to get there, there was a whole extra rotation. Okay. You can also get coterminal angles by going 360 degrees in the opposite direction. So, and then remember that in radians, that would be 2 pi. So what you're seeing here is like 90 degrees and 450, or negative 270. Those are all actually the exact same angle. You'll see them in the exact same position on that circle if you're looking at that standard position, but they are going to just be differing by either 360 degrees, positive or negative, or 2 pi radians, okay? There's an infinite number of coterminal angles, so just keep in mind that you can list them all day long. It's not just like there's only the couple that we end up writing. All right, so example 1, it says find and draw, right? We have to draw 2. But find and draw 2 coterminal angles. One is going to be positive and one is going to be negative. And so that's what we're going to start out with. First thing I'm going to do is figure out what those degree measures are, and then we will draw them. Okay. So to get those coterminal angles, if I'm working in degrees, what I'm going to do is either add 360 or subtract 360. They want me to get a positive and a negative angle. So I'm going to do both of those. I'm going to take 30 and I'm going to add 360 to get a full rotation more. That's 390 degrees. So that is a coterminal angle. But what if I took that 30 degrees and I subtracted 360 instead? If I subtract 360 instead, I get negative 330 degrees, but that will land in the exact same place because it's either a full rotation more or a full rotation less, right? So it's not going to be any different looking other than the fact that I will show it went around one extra time. So I'm going to draw two little graphs here. We're going to do one for each. Okay. If you're wondering, like, but I struggle with these angles, these 390 and negative 330, guys, remember that they are in the exact same places where 30 degrees would be. So our initial side, always going to be on the x-axis, right? And then the terminal side is going to be at 30 degrees. So this is going to be pretty little. Both of these pictures are going to look like that, but the difference is that when I show 390 degrees, what I'm going to show is that this thing opened. I'm going to grab a different color because it looks really little. But what I'm going to show is that this thing rotates, not just going up to that angle, but it's actually going all the way around and landing there. That is 390 degrees, right? We went in the positive direction counterclockwise and then landed right there. Whereas for the other one, negative 330, I'm going to start from this initial side, and we're going to go that negative direction. That's negative 330 degrees. Okay, I'm going to zoom in just a little bit, so maybe that'll be a little easier to see. Okay, but that's what we're working with there. It's the exact same thing as if I had said 30 degrees. That's what the picture looks like, but you have to include to show which way it rotated and how many rotations it did, because you can have this thing go around and round and round and round and round. Like you can have, degrees that are in the thousands or something. You can have whatever you want to. So it would just show that it rotates around a lot. Okay, look at B. Here we go. So B, we have a negative angle to begin with. But remember that for my answers, I'm going to want both a positive and a negative. So I'm still going to do the thing where I take the angle measure and I'm going to add 360. Okay, adding 360 is going to give me 210 degrees. So these were coterminal angles, right? So is this guy. I can get a negative one by subtracting 360. So by subtracting 360, I will get negative 510. So both of these angles are in the exact same position. So let's see what that looks like, right? I'm going to draw my two little things. So I've got two graphs to reference here. And then I'm going to draw my angles. Now remember, we've got a terminal side and an initial side. All of these are always going to start the initial side on the positive x. But then my terminal side, we're going to see where it opens to. Now, the easiest one to see, it might be 210 or negative 150, whichever is easier for you to see. If I was looking at it as positive 210, you think 180 would be opening up to the other side. But this needs to go 30 degrees more than that. So it would look something along these lines. Or you could think of it as going negative 150, opening this way, right? Either way you look at it, this is what the picture is going to look like. We have our initial side on the positive x, and then the terminal side is over here, 30 degrees past that 180 mark. Okay. So for me to mark these, let's make sure that we mark these well. I'm going to use my red again to kind of see that little rotation. But for the 210, I would just say this opened the positive direction. So this was 210 degrees, right? Whereas for negative 510, this opened in the negative direction and it does more than one rotation. So I'm going to go around, we're going to spiral. That is negative 510 degrees. Okay? All right, next thing. Got one more right over here. 2 pi over 3 radians. All right, so if we've got 2 pi over 3 radians and I want to get a coterminal angle, Now, you are going to have to be a little bit careful because we're going to be adding 2 pi to the 2 pi over 3, meaning you have to remember how to add fractions. So just keep that in mind, okay? If I add 2 pi over 3 plus 2 pi, it does not become 4 pi over 3. Okay, we have to get past that, guys. Go back to elementary school. Remember how to add fractions. I need to get them to have a common denominator. So really, this one is the exact same thing as if I had done 2 pi over 3 plus, instead of having 2 pi, let's write this as a fraction with a 3 on the bottom. That would have to be 6 pi over 3. 6 pi over 3 is the same thing as 2 pi. That allows me to actually see that this would be 8 pi over 3 for that answer. For me to get the negative one, let's do that 2 pi over 3. I'm running kind of out of room, but hopefully you guys are able to write small enough so you can fit this a little bit better. So the same kind of deal, we have to get common denominators. Hold on. I started writing before I used my brain. So this is going to be 6 pi over 3 again. All right, 2 pi minus 6 pi, that's going to give us 4 pi, but negative 4 pi over 3. So these are coterminal angles, okay? They're in radians, but the question gave them to us in radians, so that's what we have to go with, right? All right, so let's draw these really quick. Okay. So I got to remember what this is supposed to look like, right? If I'm looking at 2 pi over 3, you can reference back to your unit circle, but remember about the fact that a full pi would be opening up that 180 degrees, right? This is 2/3 of that. So if you think about cutting this top section into thirds, 1, 2, 3, 1 pi over 3, 2 pi over 3. It's going to be something like this. So my initial side is on the x, my terminal side is there. Now this is actually the same thing as like there would be like a 60-degree buffer in here, and you'll get used to noticing those as we do more of this stuff. But if that helps you with drawing it, maybe use that to help. Okay, so now I've got to figure out my rotations. I've got these angles drawn, but let's look at the rotations. Now 2 pi over 3, 2 pi over 3 would be just opening here. But if I'm doing 8 pi over 3, that is opening more than one rotation in that positive direction, because 6 pi over 3 would be a full rotation, okay? But 8 pi over 3 brings me back here. All right, if I was looking at the next one, negative 4 pi over 3, this is less than one full rotation. We're going in the negative direction. Negative 4 pi over 3, just like that. Okay? All right, so coterminal angles, they land in the exact same place, but you're going to see that the degree is different, or the radians are different, even though they do land in the same location. Okay? All right, let's talk about trig in the coordinate plane. Now we're going to focus first just in quadrant 1 to keep things simple, and then we are going to work our way up to a little bit more than that. So what you're seeing here is a little picture where we've got our initial side, and I've just drawn a terminal side in quadrant 1 for the time being, okay? The idea is that this ray would be going through this random point, x, y. If you have a point that this hits, then you can actually look at a distance between that point and the origin by using your distance formula or by using Pythagorean theorem, whichever one you prefer. They actually come from the same place, right? So you can find the distance between that point and the origin to get this hypotenuse that you can end up calling it a hypotenuse, because if you drop this straight down, the y coordinate right? The height there, that y coordinate is one of the legs. The x coordinate is the other leg. And so the distance between the point and that origin would be considered the hypotenuse, or in this case, we're going to call it r. That will make more sense as to why we're calling it r later on. Okay. The angle that in standard position that we're looking at is this one here at the vertex. That would be what we're calling theta in this case. And so what I want you to think about is if I was going to do sine, that's going to be opposite over hypotenuse, y over r. Okay. Cosine, adjacent over hypotenuse, x over r. Tangent is opposite over adjacent, y over x. And then you have your reciprocal ones. But this is a really nice relationship where if they give you a coordinate point, then you're going to be able to figure out trig using that, even though it wasn't technically a triangle to begin with, which I know sounds wild, but you can make that into a triangle. You see that angle, and that's getting formed. You just drop this altitude down, and it causes you to have a right triangle with those side lengths. And it does end up working for all angles. I know specifically I said here quadrant 1, but it does end up working for all angles, and you'll see that in just a few minutes, okay? So this example 2, we're going to see this problem where we are going to be doing, we're going to draw the picture because it's going to help us to have that. That will be kind of like part of our work is drawing the picture here, all right? But it says that we've got an acute angle in standard position whose terminal side contains the point 5,3. So I'm going to draw that. This is only the first quadrant, so I'm not going to bother drawing a big fat coordinate plane. I'm just going to do 1, 2, 3, 4, 5, 1, 2, 3, and then let's stick that point on there as best we can, all right? So again, this is an angle in standard position, meaning that we have one side that is opening off to the right, and then this other one is going to go through that point, okay? And they said find all 6 trig functions of theta. Now, theta is going to be this angle that's created in there. And what I can do is I can do the exact same thing y'all see in that picture above, where I can drop this altitude and I can drop this guy over here. That may help. But this right here, this side length is 3. And this one down here is 5. And this guy right here, I can figure out. So this little r, we're going to call that r. We're going to be able to find that by using either distance formula or Pythagorean theorem. Again, distance formula actually comes from the Pythagorean theorem. So whichever you prefer, you do you. I'm going to use the distance formula just because I think if you're not showing work, it might be easier to see it that way. Or if you're not drawing the picture, it might be easier to get in the habit of doing that. So if you're trying to save time and not have to draw a picture, distance formula might be a better bet here. So I'm going to rewrite what the distance formula is on here just because I have a feeling some of us might have forgotten. That's going to be x2 minus x1 plus y2 minus, oops, I dropped something, didn't I? It's supposed to have a squared on it. Okay, and we're going to plug those in. So one of our points is 5,3. The other point is the origin, 0, 0. So when I plug in my values, and we're going to call this r because I am finding the length of that section r. But when I plug in my values, I'm going to let the 0.53, I'm going to let that be my 2's, my x2 and my y2. So this would be 5 minus 0 squared plus 3 minus 0 squared. So that becomes 25 plus 9 under that square root, and this is the square root of 34. That does not reduce, so that is what it is. Again, that's the r value, okay? So right there, that is square root 34. All right, so look here. When I'm going to get my sine, cosine, and tangent, I can just follow those relationships, okay? Get a better color. It's not a good one. This will be better. Okay. So for sine of theta, whatever theta is, right? That's going to be opposite over hypotenuse. 3 over square root of 34. Again, you can look at it as the y value, which is, again, 3, over that r value, which we got to be square root of 34. Now, I do have a square root on the bottom. If I multiply top and bottom by square root of 34, I get 3 square root of 34 over 34, and I like that answer better, so I'm going to stick with that. All right, cosine of theta. That is going to be the adjacent over hypotenuse, or the x over r, right? So that's going to be 5 over the square root of 34. Again, I'm going to fix it. So if I multiply by square root 34 on top and bottom, it becomes 5 square root of 34 over 34. All right, tangent. Tangent is going to be opposite over adjacent. Opposite over adjacent, right? 3 over 5. But do keep in mind that's the same thing as the y over the x. Y over x, 3 over 5, right? And I don't have to rationalize that. It's already good. Okay, I'm going to put my others here. I'm just going to try to make them fit. That's cosecant of theta. Cosecant of theta, we're going to flip that sign one. So this is square root 34 over 3. I don't have to rationalize that. Secant, flip your cosine one. So this is square root 34 over 5. And then cotangent, we're going to flip the tangent. So this will be 5 over 3. Okay? So these are our other three. All right, we're going to try for this video to see if we can fit one more question in here, because that would be a really good breaking point. So we're going to look here at example 3. And what you're going to see is you're going to see the same kind of point, except one of those signs is different. And so I want to show you what we're going to do to get those answers, okay? We're going to use the x, y, and r in the exact same way we did the last time to be able to get our sine, cosine, tangent, all that jazz. But what I want you to keep in mind is that one of the values is going to be a negative 5. So just like on the last one, now we can redraw the picture, but I'm going to say from example 2, r is the square root of 34. Okay, this is going to be the same thing because we're using the same points, except one of them happens to be negative, but they'll be the same distance from the origin. Okay, that means x is going to be negative 5 and y equals 3 here. So this is from example 3, okay, because we're using these coordinates. But in order to get your sine, cosine, and tangent, we're going to do the exact same thing that we did before with those relationships with your x, y, and r. So I'm going to bring those back. Maybe that'll help as well. That's these guys right here. So remember that sine is going to be y over r, cosine is x over r, tangent is y over x. And we're going to follow that pattern. Okay, so I'm going to put that here, y over r. This one is going to be x over r, and tangent will be y over x. Okay, so remember how we said y here is 3, and this is going to get over r. So 3 over square root of 34. I'm going to rationalize it just like on the last one. There we go. Now this guy, cosine, we're going to we want x over r. So negative 5 over square root of 34. So when I rationalize this one, it's negative 5 square root 34 over 34. Tangent is simply going to be y over x, 3 over negative 5. Okay. To get my others, cosecant. Now that we've done all the hard work, cosecant, just flip your sign. So square root 34 over 3. For secant, we're going to flip my cosine. So this is going to be a negative square root 34 over 5. And then for cotangent, we're going to flip the tangent. So this is a negative 5 over 3. And there we have our answers. So if you get to the point where you're like remembering this relationship, y over r, x over r, y over x, it prevents you from having to draw a picture, okay? And that's kind of what we're moving to, is being able to do some of this without always doing that. Okay, all right, so fantastic. That is going to be it for part A of the 4.3 lesson, and I look forward to seeing you guys in the next one. Bye.